It is the ghost in the machine of our collective fear of the deep. A creature whose name alone, Megalodon, conjures an image of a primordial terror. A shark of such impossible proportions that it ruled the world's oceans with absolute authority for over 20 million years. This was not just another large predator. It was the largest and most powerful vertebrate predator in the history of our planet. Otodus Megalodon was a monster of a scale that strains the imagination. A shark that could reach lengths of 60 feet, 3 times the size of a large great white, and weigh over 50 tons. A freight train of muscle and cartilage. Its jaws, wide enough to swallow 2 adult humans side by side, were lined with hundreds of 7-inch serrated teeth. The perfect tools for shearing through the flesh and bone of its primary prey, the great whales of the Cenozoic era. For millions of years, from the Miocene to the Pliocene epochs, the Megalodon was the undisputed apex. It was an ecological force of nature, a hyper-carnivore that shaped the evolution of marine mammals and structured the oceanic food web around its immense appetite. Its fossilized teeth, found on every continent, are the stony testaments to its global reign. From these teeth and the few exceptionally rare fossilized vertebrae that have been discovered, we have pieced together the physical reality of this animal. We have calculated the crushing power of its bite and estimated the immense size of its body. We have, in essence, built the monster. But a predator is more than just its weapons. A 50-ton shark cannot survive on sheer size and brute force alone. To hunt effectively in the vast, 3-dimensional, and often dark world of the ocean, it requires a sophisticated set of tools for finding its prey. This brings us to a deeper, more profound mystery. For all of our knowledge about its colossal size, we are left with a ghost. The Megalodon's body, like that of all sharks, was made primarily of cartilage, which rarely fossilized. We have no fossilized skin, no fossilized muscles, and most critically, no fossilized brain or sensory organs. How, then, can we possibly know what the world looked like to a Megalodon? How did it navigate the endless blue? And how did it hunt in the dark, murky depths, where sunlight cannot penetrate, or during the blackness of night? To answer this question, to reconstruct the mind of this ancient hunter, we cannot look to the rocks. We must look to the living. We must turn to its closest living relative, the animal that carries the echo of the Megalodon's lineage in its very DNA, the great white shark, Carcharodon carcharias. The great white is not a direct descendant of the Megalodon, but they share a common ancestor, splitting off from a related lineage millions of years ago. The great white is our Rosetta Stone, a living, breathing model that allows us to reverse engineer the sensory world of its extinct giant cousin. The fundamental sensory biology of sharks is an ancient and highly conserved system. It's perfected over 450 million years of evolution. The tools a great white uses to hunt today are, in all likelihood, the same fundamental tools, albeit on a smaller scale, that a Megalodon used to hunt the whales of the Miocene. By deconstructing the extraordinary sensory apparatus of the great white, we can begin to build a picture of the Megalodon's world. We can move beyond the size of its teeth and into the realm of its perception. The answer to how the Megalodon hunted in the dark lies not in a single sense, but in a complex, overlapping, and beautifully integrated web of senses, a suite of biological technologies that made it not just a brute but a ghost, a silent and supremely aware predator. This investigation will take us on a journey through this sensory web, from the familiar senses of smell and sight, to the more alien concepts of distant touch, and finally, to the shark's true superpower, a sixth sense that allowed it to detect the very spark of life itself. To understand the giant, we must first understand its modern counterpart. We must build the sensory toolkit piece by piece, before we can place it into the mind of the ghost, and for the first time, witness the world through the eyes of the Megalodon. The hunt for the ancient predator's mind begins now. To build the mind of the Megalodon, we must begin at the outer edges of its perception. A predator of this scale, hunting in the vast, featureless expanse of the open ocean, needed a way to detect the possibility of prey from enormous distances. The first step in any hunt is simply knowing that something is out there. For this, sharks have evolved to exquisitely sensitive, long-range detection systems that are completely independent of light, making them perfect tools for a hunter that operates in the perpetual twilight of the sea. These are the senses of smell and distant touch. Let us first examine the most legendary of the shark's abilities, its sense of smell or olfaction. The trope of a shark detecting a single drop of blood from a mile away is a slight exaggeration, but it is rooted in a profound biological truth.
Ow.
The shark's olfactory system is a masterpiece of chemical detection. Unlike in humans, a shark's nostrils or nares have nothing to do with breathing. They are used exclusively for smelling. As a shark swims, water flows into the two nares, passes through a complex chamber containing a series of folded tissues called olfactory lamellae, and then flows back out. These lamellae are covered in millions of receptor cells, creating an enormous surface area for chemical molecules to bind to. The result is a sense of smell of almost unbelievable sensitivity. A great white shark can detect certain chemicals like fish oils or amino acids in concentrations as low as 1 part per 10 billion. This is the equivalent of detecting a single drop of a substance in an Olympic-sized swimming pool. It is this sensitivity that allows it to detect the scent of a bleeding seal or a whale carcass from miles away, giving it its reputation as the ocean's great bloodhound. But a shark's sense of smell is far more sophisticated than just a simple blood detector. It is a tool for reading the entire chemical story of the ocean. It can detect the subtle chemical signals of a spawning fish aggregation, the stress pheromones released by a frightened school of fish, or the unique chemical signature of a seal colony. And critically, this sense provides a direction. By comparing the strength and timing of a scent signal arriving at its left and right nares, the shark's brain can instantly determine the direction of the source, allowing it to turn and follow the scent trail in stereo. Now, let us scale this system up to the colossal proportions of a megalodon. A 60-foot shark would have had a correspondingly massive head and, therefore, a much larger and more complex olfactory system. The nares would have been larger, the olfactory chambers more voluminous, and the surface area of the olfactory lamellae would have been exponentially greater. This doesn't just mean its sense of smell was better. This means it was operating on a completely different scale. The megalodon's world was a vast, three-dimensional map of chemical information. It would not have been merely detecting a wounded whale from a few miles away. It would have been able to detect the faint, residual scent plume of a pod of whales that had passed through an area hours or even days before. It could have followed the great whale migration routes, not by sight, but by their faint, lingering chemical highways in the water. In the darkness of the deep, or the blackness of night, its sense of smell was its long-range radar, its early warning system. It's constantly sampling the currents for the chemical promise of a multi-ton meal. This was the first layer of its perception, a sense that told it, from an immense distance, that a hunt was possible. Once a scent trail placed the megalodon in the general vicinity of its prey, perhaps a large, solitary whale, like the primitive cetathea, a favorite food source, the next sensory system would come online. As the shark closed the distance to within a few hundred yards, it would begin to use its sense of distant touch, a faculty so alien to us that it borders on a superpower. This is the shark's lateral line system. Running down the length of each side of the shark's body, from its head to its tail, is a thin, fluid-filled canal just beneath the skin. This canal is open to the surrounding seawater via a series of small pores. Within the canal, spaced at regular intervals, are the sensory organs themselves. Clusters of cells called neuromasts. Each neuromast contains tiny, hair-like cilia that are embedded in a gelatinous, dome-shaped cap called a cupula. The system works on a simple principle of fluid dynamics. Any movement in the surrounding water, struggling fish, a swimming whale, or even the subtle pressure wave created by a large, silent object moving nearby creates a pressure wave that travels through the water. When this pressure wave reaches the shark, passes through the pores and into the lateral line canal, causing the fluid inside to move. This movement displaces the gelatinous cupula, which in turn bends the tiny hair cells within it. This bending triggers a nerve impulse that is sent directly to the brain. The result is that the shark can literally feel the movement of other objects in the water from a significant distance long before it can see or hear them. It is a hydrodynamic imaging system. By interpreting the complex symphony of pressure waves hitting its body, The shark can determine the size, speed, direction, and even the nature of the movement. It can distinguish the panicked high-frequency vibrations of a wounded fish from the slow, rhythmic low-frequency pulse of a calmly swimming whale. Now imagine this system on a 60-foot megalodon. Its lateral line would have been an immense sensory organ, stretching the entire length of its massive body. This vast array of neuromasts would have provided it with a high-resolution, 360-degree hydrodynamic map of its immediate surroundings. In the total darkness of the midnight zone, it would have been acutely aware of every major movement around it. It could feel the powerful, rhythmic beat of a whale's tail flukes from hundreds of yards away. It could sense the subtle change in pressure as the whale turned or changed depth. This was the Megalodon's tracking system. The sense of smell had brought it to the correct patch of ocean. Now the lateral line allowed it to pinpoint and stalk its unseen prey with unerring precision. It could match the whale's speed, shadow its movements, to position itself for the perfect attack, all without needing a single photon of light. The whale, for its part, would have been completely unaware that it was being stalked by a silent, 50-ton ghost that was feeling its every move. We have now brought our predator out of the darkness from miles away to within striking distance of its prey. The long-range chemical detection of the olfactory system has given way to the medium range. Motion detection of the lateral line, the ghost is in position. But for the final brutal act of the hunt, the attack itself, an even more sophisticated and precise set of senses is required. The next layer of the shark's perception would now take over, a sense that allowed it to see, not just with light, but with the very electricity of life itself. The hunt has reached its critical terminal phase. Guided by a trail of scent molecules across miles of open ocean, and then by the subtle pressure waves felt along its flanks, the 50-ton megalodon has now closed to within a few dozen yards of its immense prey, a Miocene whale, swimming silently through the dark or murky water. The predator is now too close for its long-range senses to be the primary tool. The final attack requires absolute precision. A miss or a poorly aimed strike would be a massive waste of energy and could even risk injury to the predator itself. For this final lethal moment, the megalodon would engage its most sophisticated and powerful sensory system, its true superpower: electroreception. This is the shark's sixth sense, a faculty so completely alien to our own human experience that it borders on the paranormal. It is the ability to detect the faint, invisible bioelectric fields that are generated by all living things. Every time a muscle contracts, every time a heart beats, every time a nerve fires in the brain of an animal, it creates a minute electrical disturbance in the surrounding water. To a shark, this is not an invisible phenomenon. It is a beacon, a clear, unambiguous signal of life. The organs responsible for this incredible sense are called the ampulla of Lorenzini, named after the 17th century Italian anatomist who first described them. Distributed in a dense network of pores around the shark's snout, head, and pectoral fins, these organs are small, jelly-filled canals. At the base of each canal is a cluster of specialized receptor cells. The electrically conductive jelly carries the faint voltage potentials from the surrounding seawater down the canal to these cells, which can then detect a voltage gradient as small as 5 billionths of a volt per centimeter. This is the most sensitive electroreceptive system known in the animal kingdom. It is sensitive enough to detect the electric field of a standard AA battery connected to electrodes a mile apart. For a modern great white shark, this sense is a crucial tool for the final moments of an attack. When a shark launches its high-speed vertical ambush on a seal, its own eyes often roll back into its head for protection at the moment of impact. It is, for a split second, effectively blind. In this critical moment, it is the ampulla of Lorenzini that guide the final precise positioning of the jaws. The shark is not biting at what it sees. It is biting at the electric field of the seal's beating heart and struggling muscles. This sense also allows it to find prey that is completely hidden from sight. A flounder buried in the sand is invisible to the eyes, but its electric field is a clear target on the shark's sensory map. Now let us scale this extraordinary system up to the megalodon. Its massive, broad head would have been covered in a vast array of these ampullary pores, a living electrical detector of immense size and sensitivity. As it closed in on the whale in the darkness, this electroreceptive grid would come alive. It would no longer be just feeling the whale's movement with its lateral line. It would be seeing its bioelectric field, a ghostly, shimmering aura of life against the dead, electric blackness of the ocean. This was the Megalodon's targeting system. It was a biological heads-up display that provided a level of detail that no other sense could match. While the whale's body might be a vague, dark shape in the gloom, its electric field would highlight the specific areas of greatest biological activity. The rhythmic pulse of the whale's giant four-chambered heart would be a powerful rhythmic beacon. The complex electrical signals from the whale's brain and central nervous system, the constant firing of the muscles that powered its massive tail flukes, would all be clearly perceptible. This gave the Megalodon a profound tactical advantage. It was not just attacking a whale, it was attacking specific, vital targets on that whale. It could distinguish the electrically hot, muscle-rich, and blood-filled areas of the body from the electrically cold, blubber-rich areas. A bite to the blubber is a wounding, energy-draining attack. A bite to the heart, the lungs, the massive locomotive muscles of the caudal peduncle, the base of the tail, is a crippling, incapacitating blow. Imagine the final moments from the Megalodon's perspective. In the near or total darkness, it has positioned itself below and behind the whale. Its olfactory and lateral line systems have done their job. Now, as it prepares to launch its attack, it switches to its amplitude. It can see the pulsing, rhythmic electrical signature of the whale's heart. It can see the powerful, firing muscles of the tail. It can choose its target with surgical precision. It ignores the thick, insulating layer of blubber and instead targets the locomotive engine. With a cataclysmic burst of speed powered by its own immense muscles, the 50-ton predator rockets upwards. Its attack is not a random bite into the whale's flank. It is a precisely aimed, devastating strike on the caudal peduncle, the 7-inch, serrated teeth, powered by the most powerful bite in history. Shear through the muscle, tendon, and bone, effectively severing the whale's engine from its body. The whale is immobilized, its primary means of propulsion destroyed in a single, perfectly guided attack. The hunt, conducted in total darkness, is over. This combination of long-range chemical sensing, medium-range hydrodynamic imaging, and close-range, high-precision electrical targeting created a predator that was perfectly adapted to a 24/7 hunting cycle in any and all light conditions. The darkness was not a hindrance to the Megalodon. It was an advantage. It was a cloak that hid its immense 50-ton body from the eyes of its prey, while its own, more sophisticated senses allowed it to move through that darkness with an unerring and lethal confidence. We have now constructed the full, non-visual sensory suite of the ghost. But the Megalodon did not hunt exclusively in the dark. It was a versatile predator that also hunted in the sunlit surface waters. To complete our picture of its sensory world, we must now turn to the more familiar senses of sight and hearing, and explore how these two were adapted to make the Megalodon the ultimate oceanic assassin, day or night. We have assembled the Megalodon's arsenal for hunting in the dark, a trinity of non-visual senses. Section the lateral line, an electroreception that worked in perfect concert to create a predator of unparalleled awareness. This suite of senses made it a master of the deep, the murky, and the nocturnal seas. But the Megalodon was not solely a creature of the abyss. Its primary prey, the great whales of the Cenozoic, were air-breathing mammals. They had to spend a significant amount of their time at or near the sunlit surface. To be the ultimate apex predator, the Megalodon had to be just as effective a hunter in broad daylight as it was in the crushing blackness. To complete the portrait of its sensory world, we must now explore its more conventional, but no less formidable senses of hearing and sight. Let us first consider its sense of hearing. In the aquatic world, sound is a far more efficient carrier of information than light. Sound travels nearly 5 times faster and much farther in water than it does in air. For a marine predator, hearing is a critical long to medium range sense. A shark's auditory system is elegantly simple and effective. It does not have external ears. Instead, it has a pair of small pores on the top of its head that lead to an inner ear where hair cells, similar to those in the lateral line, detect vibrations. More importantly, its entire body, particularly its lower jaw, acts as a conductor, transmitting sound vibrations from the water through its skeleton to its inner ear. A shark, in a very real sense. Here's with its entire body. Sharks are particularly attuned to low-frequency sounds, typically in the range of 10 to 800 hertz. This is the exact frequency range produced by the struggling, panicked movements of a wounded animal. The frantic, low-frequency vibrations of a sick, injured, or a young whale would have been an irresistible dinner bell for a megalodon, a clear acoustic signal of a vulnerable target that could be detected from miles away. This auditory sense would have perfectly complemented its sense of smell, providing a second independent stream of long-range data. A scent plume might tell the megalodon that a whale carcass is in the area. The sounds of other sharks feeding on that carcass would help it to pinpoint the location with greater speed and accuracy. Now let us turn to the final piece of the sensory puzzle, the megalodon's vision. What did the world look like through the eyes of this giant? While no megalodon eyes have ever fossilized, we can again turn to its living relative, the great white, for a powerful model. A great white shark's eye is a sophisticated and highly adapted optical instrument. The pupil can dilate and constrict, allowing it to function effectively in both the bright, sunlit surface waters and the dim light of the depths. Crucially, like a cat, a shark's eye possesses a tapetum lucidum. This is a layer of reflective mirror-like crystals located behind the retina. When light enters the eye, it passes through the retina, hits the tapetum lucidum, and is then reflected back through the retina for a second time. This process effectively doubles the amount of light available to the photoreceptor cells, giving the shark exceptional vision in low light conditions, such as at dawn, at dusk, or in deep murky water. The megalodon would have possessed these same fundamental adaptations, but on a much grander scale. Its eyes would have been enormous, likely the size of grapefruits, capable of gathering a huge amount of light. This would have made it a formidable visual hunter in the twilight hours, the very times when whales might be most vulnerable at the surface. The classic hunting strategy of a modern great white is the vertical ambush, a high-speed attack launched from the dim light of the depths towards the silhouette of a seal backlit by the bright surface. It is a visual attack, relying on the shark's ability to see its prey from below. It is highly probable that the megalodon employed a similar strategy. From a position of 100 or 200 feet down, it could have scanned the bright surface waters above, looking for the telltale multi-ton shadow of a whale. Its large, light-gathering eyes, perfectly adapted for seeing in this dusk from below, would have allowed it to lock onto its target, time its attack, and launch its cataclysmic high-speed assault. So, how did the megalodon hunt? The answer is that it hunted with a complete and perfectly integrated sensory toolkit, a web of perception that made it the ultimate all-conditions predator. The story of a megalodon hunt was a story of a seamless sensory cascade, the search long range. From miles away, the hunt began with the faintest chemical whisper in the water, detected by its colossal olfactory system, or the distant, low-frequency thrum of a struggling animal, detected by its auditory system. These senses gave it a direction, a purpose, the stock medium range. As it closed the distance, its lateral line would take over, providing a higher resolution, 360-degree hydrodynamic map of its prey's movements, allowing it to stalk the unseen whale with silent, unerring precision. The attack close range. In the final moments, its two most precise senses would come online. In sunlit waters, its large, powerful eyes would provide the visual data for a devastating ambush from below. In the dark or murky depths, its sixth sense, the ampulla of Lorenzini, would provide a perfect, high-definition, electrical map of the whale's vital organs, guiding the final lethal strike with surgical accuracy. The megalodon's reign as the ocean's supreme predator was not simply a consequence of its immense size and power. It was a reign built on a foundation of sensory supremacy. It was a ghost in the darkness and a demon in the daylight. Its genius lay in its ability to master every possible sensory domain, to seamlessly switch between chemical, mechanical, electrical, and visual data to build a complete and lethal picture of its world. The true terror of the megalodon was not just that it was a 50-ton shark with 7-inch teeth. It was that day or night, in clear water or black, it always knew exactly where you were.